All right, in this video, we're going to go through the relevant parts of the Unit 9 study guide for honors chemistry. So in the 21-22 school year, we skipped the first acquisition statement. So I'm going to actually go down and start here on the second acquisition statement, which is identify, label, and interpret energy diagrams. Okay, so if you look at the diagram here, we've got progress of the reaction labeled on our x-axis, and then I have potential energy on the y-axis. Okay, so our reactants are always on the left side, and the products are always on the right side. Okay. So we want to label a couple things on here. It says label the activation energy of the forward reaction. So our activation energy is the energy that we need to get over this hill and make it to the other side. So this is our activation energy, and we label it EA. So it's essentially the height from the amount of energy that we started all the way up to the top of that hill. The change in enthalpy is the difference between the energy of the products and the reactants. So here, we're going to label that delta H. That's the difference between them. Okay, so it says, what is the value of the potential energy of the reactants? So remember, the reactants are on the left side. So if you go and look on the y-axis, we're starting at 40 kilojoules. For the products, here, we just follow that over to the y-axis, and we're at 20 kilojoules. Okay, potential energy of the activated complex. The activated complex is at the very top here, okay? That is our activated complex. Just the top of our hill here. Okay, so if you follow that over, we're at 100 kilojoules. Okay, the activation energy of the forward reaction, so that's going to be the activated complex. So the top of the hill, minus where we started, which was the reactants. So the top of the hill, excuse me, is 100 kilojoules. We're going to subtract where we started, which was 40 with the reactants, and we end up with 60 kilojoules. Okay, it says, is the above diagram representing an endothermic or exothermic reaction? So in this case, it's exothermic. And the easy way to spot this, we want to look at the two energy values. So we are ending with less energy than we started with. So that means that energy was released. Also, our delta H value, our change in enthalpy, is going to be the delta H of the products minus the delta H value of the reactants. So our products, we were 20 kilojoules. So that's supposed to be kilojoules, minus the reactants, which was 40. 20 minus 40 is negative 20 kilojoules. Anytime our delta H value is negative, it's always exothermic. All right. Now, on to some calorimetry calculations. Okay, so calorimetry is a really cool process. So let's go up to here. Okay, so a calorimeter works like this. So in this diagram here, you can see that here it says it's a styrofoam cup. There are fancier versions of a calorimeter, but essentially we have some sort of an insulating container. We fill it with water, and it's a closed system, so we have a nice tight lid on here, and then we have a thermometer. So we're going to do a lab with calorimetry in class where we're going to have a metal. We're going to put the metal into the water after it's had a chance to heat up to 100 degrees Celsius, and we're going to see how the temperature of the water in our calorimeter changes. So the water is going to be at room temperature. We put a really hot piece of metal in there. It's going to raise the temperature of the water in the calorimeter, and we're going to use that change in temperature to figure out the specific heat value of our metal. So heat table. Every metal that we've got that we're going to be testing in this lab has a specific heat value. Okay, so if you just Google specific heat table, here's aluminum, concrete, diamond, glass, helium, water. Everything has its own specific heat value. Okay, the units are a little different here. So water typically for our units is 4.184. So it's going to be joules over grams per degree Celsius. So essentially, it takes 4.184 joules of energy to raise the temperature 1 degree Celsius for every 1 gram of water. Okay, so again, we're going to use that change in temperature value to identify the metal in the lab. So we're going to do some practice calculations here, and this is exactly what we'll do in the lab. So the equation that we use is Q equals mc delta T. Okay, that's the whole concept here. Okay, so Q is the amount of heat energy, M is the mass, C is the specific heat value, and delta T is our change in temperature. All right, now, another important thing is the amount of heat energy lost by the water, or the metal, sorry, is going to be equal to the amount of heat energy gained by the water. Okay, so that makes sense. So we're going to put this really hot piece of metal into the water. The heat is going to transfer from that piece of metal to the water, and both will eventually stabilize at the same temperature. Okay, now, since we're setting the Q values equal to each other, we can take that equation and rewrite it. So if Q equals mc delta T, I can rewrite this as negative mc delta T. So again, the metal is exothermic. The heat is going to be leaving the metal, and we're going to set that equal to mc delta T of the water. Okay, so I can label this side. This is going to be the metal, and then this will be the water. So again, the heat's flowing from metal to water. I know I threw a lot of information at you. Let's take a look at these problems. You don't always need to use the negative Q of metal equals Q of water. That's only when you use a calorimeter. For this first question, it's just asking us to calculate the amount of heat energy that must be added to raise the temperature. Okay, so unless it gives you information about the water and the metal, you can assume that we're just going to be calculating our heat energy. Okay, so let's take a look at this first equation. So copper pot has a mass of 0.5 kilograms. And we know for every 1 kilogram, there's 1,000 grams. We want to make sure our mass is in grams, so that'll be 500 grams. Our specific heat of our copper is 0.385 joules over grams degrees Celsius. And our change in temperature that's going to be the final temperature minus the initial temperature. We want to go to 125, and we're starting at 25. So that's a change in temperature of 100 degrees Celsius. So in this question, notice it's only giving us information about the copper pot. So we're only going to be calculating the heat for our copper pot, the heat energy. Okay, so we've got Q equals mc delta T. Our mass was 500. Our C value was 0.385, and then our change in temperature was 100. So let's plug this into our calculator. All right, so we've got 500, 0.385, and 100. Oof, that's a lot of energy. So we've got 19250. And our units are going to be joules. Okay, now if you look at the question, we've got, let's see, 3 sig figs, 3 sig figs, 3 sig figs, 2 sig figs. So if we round this correctly, it would be 19,000 joules. All right, number 10. An unknown metal has a mass of 1.85 and undergoes a temperature change of 68.3 degrees Celsius when 3.78 joules of heat is added to it. Calculate the specific heat of metal. All right, again, we're only given information about the metal, not about the water, so we're not using a calorimeter, so we're just going to use our Q equals mc delta T equation. So we've got a mass of 1.85 grams. It gives us the temperature change. We don't need to do any math here. Our change in temperature is 68.3 degrees Celsius. It's also giving us our Q value. It's giving us the heat. The heat is 378 joules. So in this case, we're solving for our C. Okay, so Q equals mc delta T. Okay, to get C by itself, let's divide both sides by m delta T. M delta T. So we'll end up with C equals Q over m delta T. Okay, so C is going to be equal to our Q value, which is 378 joules. We've got our mass, which is 1.85 grams. And then our change in temperature, which is 68.3 degrees Celsius. Okay, so we've got 378 divided by, now I want to make sure that my denominator is in parentheses so that it reads it as a denominator. So 1.85 times 68.3. Enter. All right. So we've got, let's see, 2.9915. All right, so 3 sig figs, 3 sig figs, 3 sig figs. We're going to round this to 2.99. And our units are going to be joules over grams degrees Celsius. All right. Now, numbers 11 and 12 are using a calorimeter. So let's look at why these questions are different. So for number 11, it says a student heated up a 20-gram block of metal and placed it into 100 grams of water in a calorimeter. If the temperature of the water increased 4.80 degrees Celsius and the metal cooled down to 49 degrees Celsius, what's the specific heat of the metal? Assume no energy was lost to the surroundings, and it gives you the specific heat of water. Okay, so big difference here. It tells you that a calorimeter is being used, so obviously we're going to use the calorimetry equation right here. Also in this question, it's giving us information about the metal and the water. So 2 ways you can easily tell. So I'm going to make a table So we've got our metal, and we have our water. So I'm going to separate out the information. Okay, so the mass of our metal is 20 grams. It's placed into 100 grams of water. Okay, in a calorimeter. If the temperature of the water increased, so that's going to be our delta T, 4.80 degrees Celsius, and the metal cooled down 49 degrees Celsius. So it's cooling down, so it's going to be negative 49 degrees Celsius. What is specific heat of the metal? So we don't know our C value. And for water, it gives us a specific heat value of 4.184 joules over grams degrees Celsius. Okay. Well, let's plug into our equation. So we have mc delta T of our metal equals mc delta T of our water. Okay, so we've got negative. Our mass is 20. We don't know the specific heat, so I'm just going to leave it as C. And then our change in temperature is negative 49 degrees Celsius. Okay, our mass of water is 100. Specific heat of water is 4.184. And my change in temperature is 4.80, 4.8. Okay. When I go to solve this, I usually just start with the right side because we've got all the information about the water here. Okay, so let's simplify that. So we've got 100 times 4.184 times 4.8. Okay, so we get 2008.32. Okay, on the left side, this looks terrible, right? We've got a negative, we've got a negative. Well, let's multiply 20 and 49. Okay, so that's 980. One of the numbers was negative, so it'll be negative 980, which was also negative. And then we still have our C on the inside. Okay, if you recall from math, negative times a negative is a positive. So we're going to have 980 times the specific heat value equals 2008.32. We want to solve for our specific heat value. C equals, so we're going to want to divide both sides by that 980. So 2008.32 divided by 980, and we get 2.049. And looking at our question, looks like every single number is, we have one that's 4. We have a couple that are 4, but we have 3 sig figs. So if I'm rounding this to 3 sig figs, it's going to be 2.05. And our units are joules over grams degrees Celsius. Okay, moving on to 12 here. A 19.75 gram sample of metal at 98.6 degrees Celsius is placed in a calorimeter containing 99.37 grams of water at 23.4 degrees Celsius. The final temperature of the metal and the water is 28.5. What's the specific heat of the metal? Assume no energy was lost to the surroundings. The specific heat of water, 4.184 joules over grams degrees Celsius. Okay. So we have to do a little bit more work here because it's not giving us the change in temperature. It gives us an initial temperature and a final temperature. So we have our metal and we have our water. Let's go through and let's collect all the information. So the mass of our metal is 19.75 grams. The mass of our water is 99.37 grams. Okay, let's see. We don't know the specific heat of the metal. We know that water is 4.184 joules over grams degrees Celsius. Okay, and then the temperature information, we have an initial temperature for our metal is 98.6 degrees Celsius. The initial temperature of our water is, let's see, 23.4. Okay, now here's the part that a lot of people get confused on. So we have an initial temperature for our metal, we have our initial temperature of our water. The final temperature of the metal and the water is 28.5. So again, if you go back to the calorimeter device, we put the metal that's hot into the water, which is at room temperature, and the temperature of the water in the calorimeter rises. The heat energy transfers from the metal to the water, and then both temperatures equalize. So when the metal doesn't have any more heat to transfer to the water, it stops, and they should be both at the same temperature. Okay, so our final temperature is going to be 28.5 degrees Celsius. All right, so we can calculate our change in temperature, delta T. That's always final minus initial. So for the metal, our final temperature, 28.5 minus 98.6 is negative 70.1 degrees Celsius. And then for our water, same thing. We've got our final 28.5 minus 23.4. That's 5.1. Okay, so we're going to use the same equation that we did before. So negative mc delta T of the metal equals mc delta T of the water. So negative, the mass of our metal is 19.75. The specific heat value we don't know. And then the change in temperature was negative 70.1. Set that equal to the other side. The mass of our water is 99.37. The change in temperature, or sorry, the specific heat value is 4.184. Running out of space here. Times the change in temperature, which is 5.1. Okay, just like before, I'm going to do all the multiplication on the right side first because I don't have any variables. So 99.37 times 4.184 times 5.1. Okay, so we got like a lot going on here. So let's see, negative 19.75 times C times negative 70.1. All right, so we got 2120. We don't want to round into our final step, 396,808. Okay, and then on the other side, let's multiply everything inside of the parentheses. So it's going to be 19.75 times a negative 70.1. Okay, so we end up with negative 1384.475. We still have our specific heat value that we need to find. So C equals 2120.396808. All right, so let's divide both sides by the negative 13 point, oh, wait a minute. Almost made a rookie mistake here. So my answer on the inside here was negative, and then we have a negative on the outside. So negative times a negative makes that a positive. You should never have a negative specific heat value. So if you do, go back and double check your calculations like I just did. Okay, so let's go back. So 2120, whoops, 2120.396808 divided by 1384.475. Okay, 1.53155. Okay, looking at our question, a lot of 3 sig figs. So let's round our final answer to 3 sig figs. So 1.53 joules over grams degrees Celsius. All right, moving right along. Okay, so we have some heating and cooling curves. Okay. So it says, use, label, and interpret heating and cooling curves. Draw a heating curve for water given the following information. Okay, and then we have like a bazillion pieces of information on the right side. Okay. The equations that we're going to use for some calculations are given, so I don't need to plot anything there. So the first thing that I would do is I'm going to go ahead and label my x-axis, which will always be energy. And we're going to use the units kilojoules. The y-axis will be temperature. And our units will be degrees Celsius. Okay, now the next thing that we're going to do, it tells us it's a heating curve. So that means that our temperature is going to go from a low temperature to a high temperature. And here we want to look for our melting points, boiling points. Your freezing point is the same as your melting point. And your boiling point is the same as your condensing point. Okay, when you go the other way. So, I mean, like for water, water freezes at 0. It also melts at 0 degrees Celsius. All right. Now, we want to make sure that when we plot this, we leave ourselves enough space below our freezing point and above our boiling point. So, we have a lot of lines here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have about 20, 21 lines. So if we go by tens, that'll give us plenty of room. And our freezing point is 0. So why don't we start at negative 40? And we're going to skip a line each time so it doesn't get too crowded here. So that would be negative 30. This is going to be negative 20, negative 10. This will be 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160. Okay. You can label every one. I prefer to skip just so it doesn't get too crowded on my axis. Okay, so next, let's add in some lines here. Okay, Cami's great because Cami has a straight line tool. So our freezing point is at 0. So what I'm going to do is I'm going to add a flat line here at 0. And I'm going to do the same thing for our boiling point, which is at 100 degrees Celsius. Okay, just like that. And now I'm going to connect the lines. So it's going to look, actually, let me use a different color here. It's going to look like this. Great. Okay. So it asks us to label some things. Anytime you have a plateau that is a phase change. Phase change is where you change states. So our first one that we labeled was our freezing point. And it's also our melting point. The second one that we labeled was our boiling point. And it's also the same as our condensing point. All right. Since this is a heating curve, we're going to start as a solid, and then we're going to melt and turn into a liquid. And then we're going to boil, and then we'll turn into a gas. Anytime we're changing our temperature, temperature is directly related to kinetic energy. Anytime we're changing our temperature, our kinetic energy is going up. Okay, we're increasing the temperature, we're increasing our kinetic energy. On the phase changes, whenever we have a phase change, that is potential energy. Okay, so we labeled the melting point, the boiling point, freezing point, condensing point. We labeled the portions of the graph when the kinetic energy is increasing. Now it says calculate the heat needed to turn 100 grams of water at 35 degrees Celsius to steam at 120 degrees Celsius. Oh boy. Well, I want to point out again that some equations were given to us here. And if you look closely, they almost look like the same exact equation. Almost. So the first equation that we have, notice it has delta T. So anytime we're raising the temperature or lowering the temperature, we're going to be using this equation right here. Okay. And another thing I want to point out, we have 3 different specific heat values. We have values for liquid, solid, and gas. We're going to use whatever value is appropriate for the line segment that we're on. And this will make more sense when we put those points on the graph. The other 2 equations are for phase changes. Okay, so our delta H of fusion, that's the one that we're going to use when we go from solid to liquid. Okay, the word fusion means to kind of like come together, and like liquid will kind of like come back together to form a solid. Okay, if you've ever seen the movie Terminator 2, love that movie. Okay, I'm going to show you. So in that movie, if you've never seen that movie, there is a metal Terminator. Okay, let me see, liquid. Yeah. So he turns into, oh, this is the best picture right here. So he can turn himself into a liquid and then bring that liquid in to form a robot. Okay, so it kind of looks like this one is back together. So he's fusing back together. So I always think of the T1000 when I'm going from liquid to solid. I'm fusing back together. Vaporization is the one that we're going to use when we go from liquid to gas. That one's a little easier. You hear the term vapor, like water vapor, you think gas. So that one's easy to remember because you're going from liquid to gas or gas to liquid. It deals with vapor. Okay, so kind of went on a tangent there with the Terminator, but it works. 16 says label the heat or calculate the heat needed to turn 100 grams of water at 35 degrees Celsius to steam at 120 degrees Celsius. All right, so let's plot those points on our graph. So let's get, so 35 degrees Celsius is right about, let's use a different color. Let's do, what haven't we used yet? How about hot pink? So here's 30, 35, right about there. And we want to go to 120 degrees. All right. So we want to calculate the amount of heat that it takes to go from that first dot on the left to the second dot on the right. Now we're not just going to calculate the change in temperature. We have to do a couple different calculations. The first calculation that we're going to do involves raising the temperature from 35 degrees to 100 degrees as a liquid. That's our first calculation. Our second calculation involves phase changing from a liquid to a gas. Our third calculation involves raising the temperature of our gas from 100 degrees to 120 degrees. So we're going to need 3 separate calculations here to answer this question. All right. So let's do this. So for our first calculation, we need to calculate the temperature, or the amount of heat energy it takes to change the temperature. So Q equals mc delta T. This one's easy to remember because it's the only equation that has the change in temperature in it. So we have 100 grams of water. The specific heat of water as a liquid is 4.184 joules over grams degrees Celsius. And then for our first calculation, we're going from 35 to 100. So it'll be 100 minus 35 degrees Celsius. Okay, so let's plug this in our calculator. 100 times 4.184 times, I'm going to use some parentheses here, 100 minus 35. Okay, we get a big number here. 27196 joules. Okay, our second calculation is that phase change. Q equals, we're going from liquid to gas, so we're going to use the mass times that delta H value for fusion. Nope, not fusion. Gas. Sorry, I was thinking about Terminator. Got a little confused. So vaporization. It's a good movie. If you haven't seen it, you should totally see it. So we've got 100 grams, and then we're going to use the vaporization value. So 2260 joules per gram. And we get, so I'm just going to add 2 zeros here, 226000 joules. And our third calculation is just raising the temperature from 100 to 120. So we're going to use our delta T value. So we've got 100 grams. Now we're going to use the value, since we're a gas, we're going to use the gas value. So 1.99 joules over grams degrees Celsius. Okay, so that's coming from right here. It tells you as a gas. And then the change in temperature, we're going to 120 from 100. Okay, so we've got 100 times 1.99 times, oops, not cosine, let's try parentheses, 120 minus 100. And we get 3980 joules. So just like when I use Google Maps to go from point A to point B, it calculates the distance that I'm driving on each street, and then to get the total distance, it adds them up. So this is kind of like Google Maps, right? So, you know, we have our 3 different streets. We have street number 1 that we go on, we have street number 2 that we go on, and then we have how far we go on street number 3. So we have 3 different values. To get the total that we drove, we're just going to add those 3 values together, and that's going to give us the total amount of energy. So we add those 3 numbers together. So 27196 plus 226123 plus 3980. 27196 plus 226123. 3980. We get 257,176 joules. All right. One more. So let me clean up my graph here because we're going to do the same thing. We're going to label first. Okay, so let me just kind of clean this up. Okay, so the question says, calculate the heat needed to turn 25 grams of ice at 0 degrees Celsius to water at 90 degrees Celsius. Okay, so ice at 0. Okay, so ice at 0 and water at 90 degrees. Boom. All right, now for the first dot, like, how did I know to put it there and not there? So just a quick review on this. At this point on my graph right here, I am 100% solid, 0% liquid. Like, my phase change hasn't happened yet. Here, I am 0% solid, 100% liquid. And then obviously in the middle, it would be 50-50. Okay, so we're going to need one calculation to complete the phase change, and then a second calculation to raise our temperature up to, 90 degrees. Okay, so for our first calculation, we are phase changing. So it's going to be the mass times our delta H, and I'm going to say it right this time, fusion, okay, like the Terminator. So we've got 25 grams of ice, and we need that delta H value for fusion, which is 334 joules per gram. Okay, so if I do that on my calculator, 25 times 334 gives me 8350 joules. And for our second calculation, we're raising the temperature. MC. At this point, so our first calculation, we phase changed over to a liquid. So now we're a liquid and we're raising our temperature to 90 degrees. So we're going to use the value for liquid, which is 4.18. So C of liquid, and then delta T. So we had 25 grams. C of liquid is 4.18 joules over grams degrees Celsius. Then our change in temperature. We're going from 0 to 90, so that's just going to be 90 degrees Celsius. 25 times 4.18 times 90, 9405. Now we just add those two numbers together to get our total energy. 8350 plus 9405. There we go. All right. Moving on. Says, calculate and explain enthalpy and entropy of a reaction. Given the following equations and delta H values, determine the delta H for the reaction. Okay, so I'm going to make this a little bit bigger here so it's easier to see. We don't need our calculator right now. Okay, so when you're working these problems, we have three different reactions, and we want to basically get this. Okay, so we want to make that out of the three reactions. Anything that exists on the product and the reactant side, when we add the three reactions together will cancel out. We're allowed to flip the three equations. If we flip them, we're going to change our delta H value. The other thing we're allowed to do is we're allowed to multiply the entire equation. And if we multiply the entire equation, we are also going to multiply the delta H value by whatever that was. Okay, so let's go through and do the first one. When I approach these problems, I always go through the given equation and I try to figure out what equations have what to see if it's on the correct side or if I need to flip it. Okay, so for example, we have this right here. Okay, so 2OF, 2. It is right here in our first equation. It's on the left side in our given equation, and it's also on the left side of that equation. So I don't need to flip it, but if you notice, there's a 2 here. So I'm going to need to multiply this entire equation by 2. And I will also multiply that by 2. Okay. Now let's see, we've got 2 sulfur. Okay, 2 sulfur is, well, let's see, sulfur's in this third equation. Same problem though. It's on the correct side, but it's only 1 and I need it to be 2. So we'll need to multiply that by 2, and we'll need to multiply our delta H value by 2. All right, and then let's see, we have SO2. That is, it's in a couple equations. It's here and it's here. Okay. Let's take a look at the last piece and then we'll see if we need to flip something. Okay, because right now the sulfurs are on the same side, but I want there to be 1. So if we look at the final piece here, that's on the right side, it's on the product side, but in that second equation, it's on the reactant side. So I'm going to need to flip this equation. And if I flip, that is going to change my sign. All right, so I'm going to rewrite these. This is a little tedious, but this is how it goes. All right, so when I multiply the equation by 2, I multiply everything in the equation by 2. Okay, so let me rewrite this. Okay, just a word of advice here. Try to line up the arrows in the 3 equations, or the 2 equations, or whatever you have. Just makes your life a little bit easier when it comes time to cancel. And I totally forgot to multiply that by 2, and I forgot to multiply that by 2. I should probably stop talking while I'm writing. All right, 2 times 2 makes this a 4. And then if I multiply my delta H value by 2, I don't have my calculator up anymore, but this is going to be negative 553.2 kilojoules. Okay, we flipped our second equation. So now on the reactant side, I'm going to have 4HF gas plus SO2. Okay, notice my arrows line up right here. Makes it easier to see what's on which side. And we flip the sign. So all I'm going to do here, instead of it being negative, it'll be positive. So 827.5 kilojoules. All right, third equation. So 2 times 1 is 2. And let's multiply that delta H value by 2. You get negative 593.8 kilojoules. Okay, so now we're looking to see what exists on the left side and the right side. Well, this exists on both sides. Forgot to put the gas in there, but there you go. What else exists on both sides? 2H2O exists on both sides. Um, 2O2 exists on both sides. Okay, now we have SO2 and then we have 2SO2. So I can get rid of all of the SO2. I can get rid of the one that's on the left side, and that will cancel out with one on the right side. So I will be left with just one SO2. Anything I didn't cross off, I'm going to carry down. So I have 2OF2, 2 sulfurs, and then we had SO2 plus SF4. Okay, I'm going to do the same thing with my delta H values, and I'll actually bring the calculator back up this time. Just a quick thing. So I'm using a TI-84 Plus, an emulated TI-84 Plus. The calculators that we use in class, the button layout is almost identical. When you're entering the negatives, make sure you're using the negative button down here at the bottom and not the subtraction button here on the side. You can tell that the negative is a lot smaller than the subtraction button. Okay, so we've got negative 553.2 plus 827.5 plus negative 593.8. Okay, we get a value of negative 319.5. Okay, I want to just point something out. This equation right here matches with the original equation that we had right here. That's how you know that you did this correct. So our answer is actually this, because the question says determine the delta H value. So we want to add up the 3 delta H values for the smaller equations that we needed to get our larger equation. All right, let's do another one. Okay, same thing. Same exact thing that we were doing before. So I'm going to approach it the same way that I did the last one. I'm going to go through the reaction, and I'm going to find where all the pieces are in the 3 smaller reactions. Okay, so I've got hydrogen. It looks like our hydrogen gas is in the 3rd equation, but again, we have 2 and we only have 1 in the equation, so we'll need to multiply this by 2. Okay, our carbon is here, but we need 2 of them. So let's multiply that by 2. It is on the correct side though, so we don't need to flip it. All right, we got oxygen. Okay, oxygen needs to be on the left side. So we've got oxygen here, here, and here. Okay, so it's on the correct side, but we need it to be 1. So let's see, we've got 2, 1, and okay, so let's skip this one for right now. I have a feeling that if we look at the 4th piece, it's going to work itself out. For the 4th piece, that needs to be on the right side. The only equation that contains that piece is the first one, but it's on the left side. So we're going to need to flip this one. Okay. So I have a feeling that flipping that is going to make all the oxygens work out. So let's see what happens when we rewrite these now. Okay, so we flip the first one, so it's going to be 2CO2 gas plus 2H2O liquid. Then we'll have C2H5OH plus 2O2 gas. And we flip the sign. So it's just going to be 875 kilojoules. Okay, the second one, we multiplied everything by 2. So we've got 2 carbons. We have 2 oxygens. And we're going to have 2 CO2 gas. Okay, multiply the delta H value by 2, and you get negative 789.02 kilojoules. The third one we multiplied by 2, so 2H2. 1/2 times 2 is just 1, so O2. And then 2 times H2O is 2H2O liquid. Multiply our delta H value by 2, gives us negative 571.6 kilojoules. All right, let's see what cancels. So our CO2 gas is going to cancel out. Looks like our H2O will cancel out. And okay, so the O2, we got 2 O2 here, 2 O2 here, and then we're just left with O2 on the left. And I think that's it. So let's add these together now. So we've got, let's see, 2H2. We have 2 carbons. We have O2. And then on the right side, we just have C2H5OH liquid. And let's go ahead and add up our 3 delta H values. So we have 875. We have negative 789.02. And then we have negative 571.6. All right, so negative 485. Negative 485.62 kilojoules. And that's going to be our answer right there. All right. 20. Oh, this looks complicated, but it's not. 20 says calculate the change in enthalpy for the following reaction. Okay, so to find our change in enthalpy, we're going to take the sum of the moles, that's the N, times the delta H values of the products. And then we're going to subtract the sum of the number of moles times the delta H values of the reactants. For this example here, all 3 of these have a coefficient of 1. So we don't need to multiply these by anything. So we can ignore the 1, or we can ignore the N in our equation here because they're all 1. All right, so our product is MgCO3. So that's going to be negative 1096.0 kilojoules. If we had, a 2 in front of that, it would be times 2, or a 3 would be times 3. But since it's 1, it's just going to be by itself. And then we're going to subtract. This is important. Make sure if you have more than one thing on the reactant side, you use parentheses so your negative will distribute correctly. So we have MgO negative 602, and then we have negative 393.5. Okay. This is going to be a little tricky to enter on our calculator, so I'd like to show you how it works. So again, don't confuse the negative and the subtraction buttons. If you're not so good with negatives, like here, plus and negative would be the same as subtraction. If you're not so great with negatives, just do plus and minus, or plus and negative. So negative 1096 minus parentheses. The parentheses are super important. The negative should distribute to both terms. Okay, negative 602 plus a negative 393.5. Okay, so our answer was 100.5 kilojoules. All right. Let's see. The current petrochemical economy is based on the combustion of fossil fuels, of which octane is a typical example. The equation is as follows. Calculate the heat of combustion of octane using the supplied heat of formation data. Okay, this is great because we have some coefficients here. Okay, so this is the same thing that we just did, but we have some coefficients. So we're going to be multiplying things here rather than just putting the values in. So our delta H of the reaction is, again, the sum of the products minus the sum of the reactants. Okay. So we have 16 moles of our CO2, and CO2 is negative 393.5. Actually, that should probably be in parentheses. Plus, we have 18 moles of H2O. H2O's value is negative 285.8. So that's our products. Now we're going to do the same thing for the reactants. So we have 2 moles of C8H18. So 2 times negative 249.9. Okay. And we have 20 moles of O2. Now, if you look at the data table, O2 is not on there. Okay. So O2 doesn't have a value. We don't need any, it doesn't take any energy to make O2 because it's in its standard state. So we don't have a value for it. So it's just going to be 25, if you want to really write it out, 25 times 0. So that'll be 0. Okay, that looks absolutely terrible to put in our calculator. Okay, so type it in exactly like you wrote it. Okay, so the brackets are just going to be an extra set of parentheses. So bracket or parenthesis 16 times negative 393.5 parenthesis plus parenthesis 18 times negative 285.8 parenthesis, and notice there's 2 here, minus, we have 2 here, parenthesis 2 times negative 249.9 parenthesis plus parenthesis, let's move this over. I'm going to go ahead and just type this in. So 25 times 0, parenthesis, and there's 2 of them, parenthesis. Okay, so there is our answer. So we have, what was it, negative 1094.6 kilojoules. All right, moving right along. 22. Okay. 22 says calculate delta H and delta S for the reaction. So delta H is our enthalpy, delta S is our entropy. Okay. These equations are almost the same exact thing. Okay. So we're gonna just do the same thing that we were just doing, but the values, we want to make sure that we're using the correct values. So enthalpy are the delta H values. Entropy is delta S. All right. So for delta H, products, there are 2 moles of NH3. NH3 is negative 46.11 minus the reactants. Well, if you notice here, there's 2 zeros, so it'd be minus 0. So 2 times negative 46.11 gives us a value of negative 92.22 kilojoules. Okay, for delta S, our entropy, we didn't get as lucky. We've got numbers for everything, no zeros. Okay, so products, so 2 times our NH3. Our NH3 value was 192.45 minus the reactants. So we have N2. Okay, it's just by itself. So N2 is 191.61 plus we have 3 moles. 3 moles times hydrogen is 130.68. Okay, 2 times 192.45 minus parenthesis 191.61 plus parenthesis 3 times 130.68, 68, not 67, and close it up. Okay, so we get an answer of it was negative 198.75 joules per Kelvin. Okay, now you may not have noticed it, but we have kilojoules and we have joules. We want them both to be in the same units. We want them both to be in kilojoules. Okay, so to convert, we're just going to divide by 1,000 or move the decimal place 3 places to the left. So we get negative 0.19875 kilojoules per Kelvin. Okay. Now, the reason we want to make sure that they're both in the same units is for our free energy. Okay, so 23 says calculate free energy delta G at 25 degrees using the values of delta H and delta S in problem 22. Determine if the reaction is spontaneous or not. Okay, so our equation for our energy, delta G, is equal to delta H minus the change in temperature times delta S, or times the temperature, or minus the temperature times delta S. All right, so let's plug in all the values that we have. So delta H is negative 92.22. our temperature. Okay, so we cannot use degrees Celsius here. We want to convert this to Kelvin. Okay, so we're going to take our degrees Celsius and we're going to add, it's always this number, we're going to add 273 to that number, and that will give us our answer in Kelvin. Okay, our answer is going to be 298 Kelvin. All right, so 298 Kelvin times our delta S value, which was negative 0.19875. All right, let's plug this all in. Negative 92.22 minus 298, and we have negative 0.19875. And we got an answer of negative 32.99 kilojoules. If our answer is negative, it's going to be spontaneous. If it's positive, it would be non-spontaneous. Okay. Determine if the reaction is spontaneous at 500 degrees Celsius using the values in number 2 to calculate the free energy. I think it's asking us to use the values from the previous question, not number 20. It should probably say 23, not number 2. Okay, so same equation. We're just going to change our temperature. 500 plus 273 gives us 773 Kelvin. All right, so delta G. Delta H is negative 92.22 minus new temperature, 773, and then negative 0.19875. So the only thing I need to change here is the temperature. So it's going to be 773. And we get an answer of 61.41 kilojoules. It's positive, so this is going to be non-spontaneous. All right, last question. Calculate delta G, 25 degrees Celsius, if delta H is 28.05 kilojoules, delta S is 108.72 joules per Kelvin, and determine if the reaction is spontaneous or not. Okay, so we need to convert this to Kelvin. 25 plus 273 is 298 Kelvin. And we also need to convert this to kilojoules. So this will be 0.108. We're dividing by 1,072 kilojoules per Kelvin. Now we can plug in. Delta H is 28.05 minus the temperature, 298, and our delta S value, 0.10872. .05 minus 298 times 0.10872. All right, we got negative 4.34 kilojoules. It's negative, so it's going to be spontaneous. And that is the study guide. Good luck on the test.